Hello everyone, welcome to the CVPR 2020 tutorial on video modeling. I'm Yuanjun from AWS. Today I'm going to give you a brief introduction to human activity understanding in videos. In this talk, I will talk about the problem of human activity understanding from 4 aspects. I will start by reviewing the datasets and the common data sources of this problem. Then I will introduce the various tasks that are related to human activity understanding in videos. Then I will talk about some typical and popular models people use to solve this problem and some common methodology in modeling the spatial temporal information in videos. At the end, I will talk about the open questions, challenges, and the problems in current research. To understand a computer vision problem, the first thing is to look at its inputs. The inputs to the human activity understanding problem come from multiple forms. For example, there can be videos, and even images capturing different people's activities, and other signals like skeleton data that's coming from the post-estimation algorithms, and the sensory data that's coming from your iPhone or your iWatch. And also, these videos can come from multiple sources, like YouTube videos, and they can also be surveillance videos, or just some performed videos that's controlled collected. In this talk, we will mainly talk about video as input and a bit on the skeleton data, as they are derived from the videos. As we can see, the video contains rich information like space-time interaction and motion information, but they also pose huge challenge to the computation and the storage. In the model section, we will see how people tackle these problems and harness the information in videos from multiple aspects. For video as input, there are multiple datasets we can use for research. In general, these datasets can be categorized into 2 streams. The first is controlled collection datasets, and second is generally called in-the-wild datasets. Controlled collected datasets are usually provided by asking human performers to perform the actions. This approach was used in early days of action recognition research because at that time, the internet sharing of videos is not mature, so it's not very easy to find a lot of videos for research. And these datasets are usually small. But in recent days, we have actually seen a return of this approach because the controlled collection can help us remove the bias and overfitting to the background, which is quite common in the wild datasets. In the wild dataset, on the other hand, are collected from videos that were not originally designed for action recognition uses, and are mostly annotated by human annotators for their action labels or some other meta-information. The sources of videos can be movies, YouTube videos, or surveillance footages. These in-the-wild videos contain a lot of content variations and poses strong challenges to action or activity understanding algorithms. And it's also easy to collect a lot of videos because the current sheer volume of YouTube videos available online. So they are currently a very popular method used for creating datasets. A lot of recent large-scale human activity understanding datasets are built from YouTube videos. Another aspect of activity understanding are the categories of activities. From this slide, we can see a brief breakdown of household activities, which are quite complex. So a good activity understanding dataset is expected to contain a lot of categories, as well as a lot of samples for each category. Here, let's have a brief review of the number of classes and number of samples per classes for different activity understanding datasets. From this graph, we can see that recent large-scale datasets has improved these 2 aspects. We have hundreds of classes and thousands of samples per classes. We have hundreds of classes and thousands of samples per class. This means the models can learn from a large variation. This means it is possible for deep learning algorithms to learn from the large intra and inter-class variations and produce good representations for videos. And these representations can be used for various tasks of activity understanding, as we will present below. Okay, with the idea of data used in this research field, let's look at the task people are interested in human activity understanding. In my understanding, there are 3 basic levels of problems in activity understanding. The first is action classification, which deals with the question of what, or what is the activity this person is performing. And second is temporal action detection or localization, which deals with the problem of when, or based on the action classification result, we also want to know when did the action start and end. And the third level is spatial temporal action detection, which asks to the question about where. That is, in the video frame, which person is performing the activity, and what is the activity, and when did the activity start and end. Based on these 3 basic questions, we can have multiple extension of activity understanding problem by setting different problem settings. For example, we can have an algorithm that deals with online videos instead of offline or stored videos. Also, we can change the supervision and use unsupervised learning method to deal with video representation. Or we can look at multiple persons' activities, like handshaking instead of single person. And we can change from the single independent categorical labels to natural language description of videos, and even use natural language to retrieve the video segment that we're interested in. Let's look at the most basic task, video action classification. This problem has a very simple definition. Given one video as input, we want to have one label as the model prediction. For example, here we have seen the person surfing in the video. By having our models looking at this video, we want the model to predict the label surfing. So this is the definition of video action classification. That is one video as input and one categorical label as output. Although the definition is simple, the solution to this problem is actually not very trivial. As we mentioned, there is rich information in space and time recorded in the videos. How to effectively and efficiently extract them and provide the prediction is a core research challenge, and this problem has received the most research attention in the community. Regarding this problem, there is one important problem setting that I need to mention. That is the trimmed video versus untrimmed video. A lot of datasets like UCF11, HMDB, or recent kinetics and something datasets are built from trimmed videos. That means human annotators have already removed the part of the videos that are irrelevant to the labels. And the other side of the problem is untrimmed video classification. Some datasets like ActivityNet and Tumors are built from annotating untrimmed videos, and the irrelevant part is still kept in the datasets. So an algorithm for untrimmed video classification has to also take into consideration that there are irrelevant information in the video that has to be removed from prediction. And for trimmed video classification algorithms, although they have achieved very high accuracy, it's important to keep in mind that this accuracy comes from. It is important to keep in mind that this algorithm don't need to deal with irrelevant information, so their real-world application is somehow limited. So their real-world application needs additional treatment to deal with the irrelevant information that is common in videos. Another aspect of the problem is single person versus multiple person. For single person action classification, there is no interperson interactions. For example, here the surfing videos, we only have this single person performing the surfing. But for multi-person and group action classification, there is important information in the interaction between different people and the configuration they pose between each other. For example, here we have a crowded scene on the left, and on the right there are a scene of 2 people shaking hands. These different situations may need different processing of the activity understanding model, and are often considered as different domains of research. But recent datasets usually contain both of them in the categories. Now let's look at the next level of question, the temporal action detection and localization. The input to this problem is an untrimmed video, which contained informative and irrelevant parts of information. And its output are two things. The first is action labels, and second is start and end timestamps. For example, here we have a long video which contains a lot of instances of long jump. An algorithm may make predictions on where these action instances happen. Algorithms for this problem has a lot of real-world applications. For example, when you are watching a sport video, you may only care about the highlights, which are often instances of activities. And the algorithm for this problem can be used to automatically compile this highlight for you to view. The challenge for this problem is then how to accurately localize the boundary of activity instances. We want to remove all irrelevant segments, but keep all highlight parts of the videos. One challenge in collecting datasets for this problem is the high labeling cost. An annotator has to watch the entire video and go back and forth in time to exhaustively annotate all the instances in the video, and do not ignore anything that is possibly an activity instance. It hinders the large-scale collection of data, which motivates people to think about other ways, for example, weakly supervised temporal action detection. In the weakly supervised setting, the labels are just categorical. There is no temporal boundaries of instances. The models are expected to learn only from labels and make temporal action detection predictions. In this way, we can utilize the large volume of videos available to train the models. And this problem has drawn increasing research attention recently. The input for this problem is still a video. The output can be in two styles. First, we output action labels, person tracks, and start and end time of the activity instance on each person tracks. In the second style, we don't care about the identity of the person, so we only output action labels on each person bounding box at every frame of the video. This problem requires the cooperation of multiple models, like person detection, person tracking, and activity understanding. With the recent advances in these fields, more and more researchers are starting to look at this problem. For the two detection problems described above, it's also possible to formulate them as segmentation problems. For example, temporal segmentation. In this problem, we don't care about the instance. We just output action label at each frame of the video and its confidence. And for spatial temporal segmentation, the output will be segmentation masks, for example, instance segmentation of the person, and activity corresponding to this mask. So it's similar to the spatial temporal action detection, but the instance segmentation is used as the output. Now we have looked at the three different levels of questions and problems in human activity understanding in videos. Let's look at an important problem setting here, that is online versus offline. In the problems we described above, we always assume that the videos have been recorded, which means we are analyzing the observed content of the video. But in real-world application, there is always cases that the action recognition or activity understanding has to happen in the real-time manner, for example, in robotics. So this raises the question of online or real-time activity understanding. Under the online setting, the model has to make prediction based on whatever has been observed. We cannot get access to the future information in the prediction. There are two key points of online activity understanding. The first is that we cannot modify the previous prediction after observing future information, because there might be action that already performed based on the previous predictions. The second key point is the prediction usually has to be made when the model received the latest frame, so some real-time decision can be made with minimal latency. Next, if based on currently observed information, we want to make prediction on what will happen in the next, That will be the problem of action prediction and anticipation. This is very useful in applications like smart home and robotics, where an agent can prepare for the events that's going to happen in the near future. Now we have covered most tasks in activity understanding in videos. Let's spend some time to look at important and popular models for these tasks. Before the emergence of deep learning, people have already started to look at this problem of human activity understanding. There are a lot of works proposed to deal with this problem, and the most representative of them are handcrafted spatial temporal features like space-time bag-off features, dense trajectories, and its improvement version, improved dense trajectories. After the emergence of deep learning, there are a lot of works utilizing deep neural networks to extract video representations, and this work includes using convolutional neural networks, recurrent neural networks, and graph neural networks to represent the rich information in videos. I will introduce the dense trajectory method for handcrafted video features. It started by forming a set of trajectories using the optical flow between frames, and then on these trajectories, it encodes the traditional handcrafted local features such as shift, hog, or motion history, and use feature encoding to produce high-level representations, and use this representation to perform action classification. And its improved version, improved dense trajectory, use some method to correct the camera motion and use a human mask to center the feature extraction in the regions around the person. In this method, there are several important messages. The first is that low-level motion information like optical flow can be a very good source of information for activity understanding. And second is that trajectories formed by these low-level motion cues can be also a good source of information for activity understanding. We will later see how these messages can be reutilized in the era of deep learning. First few approaches towards this problem using deep learning all focus on the snippet level. A snippet is formed by one or few frames, usually below 20 frames, and they use video classification as a task to help the model learn video representations. The important works include deep video, two-stream CNN, and 3D convolutional neural networks. These approaches are very straightforward. The input to them is a one or few frames which form a snippet. They are fed through the convolutional neural networks, either 2D or 3D CNN based, and make final prediction of a category label. The two-stream CNN approach uses the idea of using optical flow to represent motion and propose this two-branch design. The first branch, the spatial string convnet, just take as input a single frame and output categorical label. The second branch, the temporal string convnet, take as input a stack of multiple frame optical flow. It considers the multiple frames optical flow as a multi-channel image and feed that through a standard 2D convnet. The output of these two branches are combined together to make the final decisions. Utilizing the idea of using optical flow to represent motion, this method, two-stream CNN, when it's published for the first time, achieved the same level of accuracy on the UCF 101 dataset as the best handcrafted features method, the improved dense trajectory, which led to the boom of deep learning method in this problem. 3D CNN-based methods achieve the modeling of space and time from a different way. It considers multiple consecutive frames of videos as a space and time volume, which has 3 dimensions, similar to the 2D convolution which we run on the image plane. It runs a 3D convolutional filter and slides that through the 3D volume to perform 3D convolution. By stacking multiple 3D convolution layers, it forms a 3D convolutional neural network and use it to make the prediction of action categories. It was first proposed in 2013. It was haunted by the lack of data to train the models because of its large number of parameters. In 2015 and 2017, it was finally popularized by the success of C3D and I3D method, which introduced large datasets and some modifications to learn from image-based convolutional neural networks to help the training of the 3D scenes. With these methods for modeling snippet-level information, it is natural to ask, can we model longer timespan? Because a video does not contain only one or few frames, it can contain hundreds of thousands of frames, and we want to model the information in the whole video instead of the single snippets. A very straightforward method is to utilize recurrent neural networks, which comes in the long-term recurrent convolutional networks work. It just combines the CNN and RNN. It uses CNN to extract information from one snippet and feed the information from the consecutive snippets to an RNN to make prediction on the whole video. Another idea for modeling long-term information is just to extend the temporal dimension of 3D scenes. For example, from the original 16 frames, later works proposed to extend that to 64 or 128 frames. But these two approaches, either using RNN or a long-term 3D convolution, both have one issue. That is, even if we have 128 frames, that is only 4 seconds in video time. How can we model videos that have 20 seconds, 1 minute, or even longer? Our current devices cannot hold that many frames in its memory. An idea was proposed in 2016 to solve this problem. That is, instead of densely sampling the consecutive frames, we can utilize the slowness of content change in videos to just sparsely sample the frames. This work, called temporal segment networks, split a video into a fixed number of sections in the training, and sample frames from each segment, and combine the prediction from multiple segments to make the final decision. It reduces the cost of training on long videos and allows the model to take full video content into consideration during training. This idea can also be used in other tasks like spatial temporal. This idea can also be used in training models for other tasks like temporal action detection or spatial temporal action detection. The methods we have described always use regular convolution to process frame information. But we know that the content of videos keep changing. Things like number of people, number of objects, and the configuration of the scenes change over time. So can we use something that's not as rigid as this regular convolution to deal with the information in video? The answer is yes. Basically, there are two approaches that take this into consideration. The first stream of work is attention-based, and second is graph convolution-based. For attention-based method, the basic idea is to use the attention mechanism, which is introduced lately, to let each pixel in the feature maps to extract information from its neighbors in space and time unevenly. The first typical work is the non-local CNN, which uses a self-attention mechanism to extract information related to each pixel in the feature map. And the second type of work is the post-guided attention. Because we know that people is important in activities, and they are the agent that perform the activity. So the pose or the skeleton of people are of important information. This method uses pose as the guidance for attention mechanism to extract information. Now we have briefly reviewed models for video modeling and activity understanding. I want to spend the remaining time to discuss with you the challenges, open questions, and problems in this research field. The first challenge, of course, is to keep improving the accuracy of models for the task we have described. But we also need to consider the efficiency of these models. If our model runs very slow on videos, the sheer volume of video available will make our deployment of models very difficult. And people care this very much. I was frequently asked by people, can we recognize action from compressed videos? So even decompressing the video can be a concern. How can we not care about the efficiency of the video models themselves? The other challenge is about the generalization of our video models. A question like, can our models work on new domains, is not yet answered. We have large-scale video datasets, but these datasets usually come from a few narrow domains, like YouTube videos or web sharing videos. How can we apply the models trained on these datasets to different domains? It's becoming a real challenge as the proliferation of video modeling technology. First, for the efficiency, to make video models run faster, people start to think about the input to the video models. We have seen works utilizing motion vectors, which are already provided by the video encoders, and RGB differences, which can be simply computed by subtracting two consecutive frames, or integrated optical flow networks to replace the computation-heavy optical computation in the two-stream CNNs. On the efficiency of the video model themselves, we have seen recent advances in the 3D convolutional neural network domain. There have been works like pseudo 3D convolution, decoupled 3D CNN, which both reduce the computation overhead of 3D convolution by replacing them with a separated 2D convolution on the frame domain and the temporal convolution on the time domain. We have seen recent works that try to combine 2D and 3D CNNs, such as the ECO work, which tries to reduce the computation overhead of low-level feature extraction by only using 3D convolution on the higher-level feature maps. On the other hand, we need to push the generalization ability of video models, because human activities are compositional and fine-grained concepts. You can have a lot of activities of playing instruments, each of them, like playing violin, playing piano, playing flute, are just different by the instrument they use. Some other activities are only different in the minor differences in the change of postures of people over time, such as gymnastics. How can our models generalize to these use cases? Recently, there have been a few new datasets proposed for fine-grained action recognition and action recognition out of context, which may shed light on this problem. Okay, we have looked at the human activity understanding in videos from all these aspects. Let's conclude today's talk with a few thoughts on the future directions. First, for data, can we keep collecting larger and larger datasets? And can the computation resources for research labs keep up with this growth? And for the models, can we find more efficient and more accurate model architectures? Can we find better approaches to spatial and temporal modeling, or even better motion representation? Also, with the emergence of architecture search, will actor search shine in the activity modeling domain? For applications, a lot of entertainment, human-robot interaction, and many other fields are calling for new models and new approaches in activity understanding. I truly believe this research field will continue to shine and thrive in the years to come. Thank you and hope you enjoy the rest of the conference.